On Monday afternoon, a rock the size of a building will pass between you and the moon, and almost nobody will notice. That part is fine. The asteroid is called 2026 JH2, and it misses us. Here is the part that should stop you. We did not know it existed a month ago. We found it days before it arrives. Days. And it is not arriving alone. There is something else moving through near-Earth space this week, a pattern in the data, and once you see what that pattern is, the word safe in every headline about this flyby starts to read very differently. Because safe this time does not mean what you think it means. Stay with me, because by the end of this you will understand the one thing the mainstream coverage refuses to say out loud, and why it has nothing to do with whether this rock hits us. If this has you hooked, like this video, and subscribe to the Sky Lab, because this is a thread we're going to keep pulling as it develops. Also drop a comment with where in the world you're watching from. Now, let's get into it. Part 1. The rock we almost didn't see coming. On Monday, a rock somewhere between 50 and 100 feet across is going to pass between you and the moon. Not at the moon's distance, closer, about a quarter of the way out. And here is the part that should stop you for a second before you scroll past it. We did not know this object existed a month ago. We did not know it existed 2 weeks ago. Astronomers found it days before it arrives. Days. Not years, not months, not even weeks. The asteroid is called 2026 JH2, and the story being told about it in the headlines is a calm one. Newly discovered asteroid will make a close but safe pass by Earth, and that is true. On the narrow question of whether this specific rock is going to hit us, the answer is no. The orbital math says it misses, but the calm version of this story is hiding the actual story, and the actual story is not about this rock at all. It is about the fact that a 50 to 100 foot asteroid was able to get this close, and the only reason we know about it is that somebody happened to catch a faint smudge of moving light in a telescope a few nights ago. If that smudge had been on a slightly different path, the path that ends here instead of sliding past us, we would have found out at exactly the same time, and we would have been able to do exactly nothing. That is what this video is about, not the asteroid, the warning. And whether the warning we get is worth anything at all. Let me give you the hard numbers first, because the numbers are what make this real. 2026 JH2 reaches its closest point to Earth on Monday, May 18th, at around 21:23 Universal Time. That is mid-afternoon in the eastern United States. At that moment, it will be approximately 56,700 miles from the center of our planet. Some of the orbital solutions put it a little farther, some a little closer, but that is the number to hold in your head. 56,700 miles. Now, to understand whether that is close, you need something to compare it to, and the obvious comparison is the Moon. The Moon orbits Earth at an average distance of about 238,000 miles. So this asteroid is passing at roughly 1/4 of the distance to the Moon. It is crossing deep inside the Moon's orbit. And here is a comparison that almost never gets mentioned, because it sounds like science fiction, and it is just arithmetic. We have a ring of satellites in what is called geostationary orbit, the communications and weather satellites that sit fixed over one spot on the planet. That ring sits at about 22,000 miles up. 2026 JH2 at 56,700 miles is passing outside that ring, yes, but it is passing closer to Earth than a huge amount of the hardware humanity has flung into deep space over the decades. It is threading through the neighborhood. It is not a distant speck, it is a visitor crossing the yard. How big is it? NASA's Jet Propulsion Laboratory estimates somewhere between 50 and 100 feet across. And I want to be honest with you about what that estimate actually is, because the honesty matters for everything that comes later. That 50 to 100 foot range is not a measurement. Nobody has put a radar beam on this object yet. Nobody has measured its heat signature. The size estimate comes from one thing and one thing only: how bright it appears in the telescope. You take the brightness, you make an assumption about how reflective the surface is. Dark rock reflects less, lighter rock reflects more, and you back out a size. That is the standard method for every newly discovered asteroid, and it always carries a wide error bar until something more precise comes along. So when you hear 50 to 100 feet, what you're really hearing is a faint moving dot, and our best guess based on how faint it is. The uncertainty is baked in. We are sizing a thing we found 4 days ago by how dim it looks. so is 50 to 100 feet dangerous? Here is where you have to resist two opposite mistakes. The first mistake is to hear asteroid and picture the dinosaurs. This is not that. An object this size is not a planet killer. It is not a civilization ender. It would not crack a continent. The second mistake, though, is the more common one, and it is to hear 50 to 100 feet and think, oh, a rock. That is basically nothing. That is also wrong. Let me put this object in a reference class you will actually recognize. In February of 2013, an object came in over the Russian city of Chelyabinsk. It was roughly 60 feet across, right in the middle of the size range we're talking about for Monday's asteroid. It did not even hit the ground. It exploded in the air, what we call an airburst, and that airburst blew out windows across 6 cities and injured around 1,500 people. Almost every single one of those injuries came from flying glass, from people standing at their windows looking up at the bright streak in the sky when the shockwave arrived and turned every pane in the city into shrapnel. 1,500 people hurt, from a rock the size of the one passing us on Monday, and it never even touched the surface. So no, 50 to 100 feet is not the end of the world, but it is not nothing. It is a city's worth of broken windows. It is a serious chunk of rock moving through near-Earth space at thousands of miles an hour, and if the trajectory had been different, Monday afternoon would have looked very different for somebody. There is one more piece of the basic profile, and it is the piece that connects to the larger pattern we are going to spend this video unpacking. 2026 JH2 has been classified as an Apollo-class near-Earth object. That sounds technical, so let me make it plain. Apollo-class asteroids are objects whose orbits cross Earth's orbit around the Sun. Picture our planet's path around the Sun as a lane on a racetrack. Most asteroids stay in their own lanes, out in the asteroid belt well away from ours. An Apollo-class object does not. Its elliptical path swings across our lane. It spends most of its time farther from the Sun than we are, but the geometry of its orbit means that periodically it cuts across the exact stretch of space that Earth also has to travel through. That is what makes this class the one that matters. Apollo asteroids are the most populous of the orbit types that can actually intersect us, and they are responsible for most of the close approaches and most of the actual impacts in Earth's history. 2026 JH2 is not an exotic object. It is a very ordinary member of the single most consequential population of rocks in the inner solar system. And I want to dwell on that word ordinary for a moment, because it is doing a lot of quiet work. When most people hear the word asteroid, the mind reaches for something rare, something singular, an event. But an Apollo-class near-Earth object crossing our orbital lane is not an event in that sense. It is a category. It is a population. There are a great many of them, and the crossing of Earth's orbit is not a dramatic exception to their behaviour. It is the defining feature of what they are. When you understand that, the framing of the news story starts to feel slightly off, because the news story treats 2026 JH2 as a discovery, a one-time curiosity, a thing that happened. And it is more accurate to think of it as a sample. A single drawn example out of a vast, mostly unseen population, and the only thing that made this particular member of the population visible to us is that its sample moment, its turn crossing our lane, lined up with a telescope being pointed in roughly the right place at roughly the right time. Change nothing about the rock and only change our luck, and 2026 JH2 is just another uncounted object that passed in the dark and was never named. That is the frame to carry into the rest of this, not a discovery, a sample, and a sample tells you about the population it was drawn from. It is also worth being precise about the speed, because speed is part of what determines what one of these objects does if it arrives, and it is part of the pattern we will trace through the whole video. 2026 JH2 is moving relative to Earth at something in the range of 9 kilometers per second. That is its closing speed with respect to our planet, and it is worth translating, because kilometers per second is not a unit anyone has intuition for. 9 kilometers per second is in the neighbourhood of 20,000 miles per hour. That is the speed at which this object and Earth are moving with respect to each other as it threads past. And by the standards of near-Earth objects, that is actually on the gentler end. These objects can close on Earth anywhere from a handful of kilometers per second up to 30, 40, and in the most extreme recorded cases far beyond that. The kinetic energy an object carries scales with the square of that speed, which means a faster rock of the same size hits very much harder than a slower one. So 2026 JH2 at around 9 kilometers per second is not the worst case version of itself. It is a moderately sized object moving at a moderate closing speed, and it still belongs in the same conversation as Chelyabinsk. That is the reference frame. Even the unremarkable members of this population are not harmless, and 2026 JH2 is, in almost every measurable way, an unremarkable member of this population. So who found it and when? The discovery came from astronomers working across multiple facilities, and two of them are worth naming because of what they tell you about how this works. One was the Farpoint Observatory in Wabaunsee County, Kansas. The other was the Mount Lemmon Observatory up in the Santa Catalina Mountains north of Tucson, Arizona. These are not secret government installations. These are working observatories, part of the network of telescopes around the world that quietly scan the sky every clear night looking for exactly this: faint moving points of light that were not there the night before. They caught 2026 JH2, they reported it. The orbital math got worked out, and the result was a confirmed close approach. And the entire window, from first detection to closest approach, is measured in days. I want to slow down on how that detection actually happens, because the mechanics of it explain so much of what follows. An object like 2026 JH2 does not announce itself. It is not glowing. It is not transmitting. It is a dark rock, reflecting a small amount of sunlight, and from Earth, it appears as nothing more than an extremely faint dot, fainter than the faintest stars most people have ever seen, buried in a field of millions of other dots. The way a survey telescope finds it is by taking repeated images of the same patch of sky, minutes apart, and then letting software compare those images. The stars do not move between frames, the galaxies do not move. But an asteroid, something close and in motion relative to us, shifts position from one frame to the next. It is a dot that walks. The software flags the dots that walk. An astronomer or an automated pipeline confirms it is real, and not a glitch, and then the position measurements get reported to the global clearinghouse that collects them. Once there are enough position measurements spread over enough time, the orbit can be calculated, and only then, only after that whole chain has run, do you get a number for how close the object will come and when. The chain is elegant and it works, and the people who built it and run it are doing real and careful science. But notice the dependency at the very front of the chain. Everything downstream, the orbit, the close approach prediction, the headline, depends on the dot being bright enough to walk into one of those images in the first place. If the dot is too faint or in the wrong part of the sky, the chain never starts. The object is not missed in the sense of being overlooked. It is missed in the sense of never having been detectable at all, and the timing of when in that chain 2026 JH2 entered is the whole point. It did not enter the chain a year ago, with its orbit slowly refined over many months into a confident long-range prediction. It entered the chain a few nights ago, when it finally got close enough and bright enough to become one of those walking dots. From first detection to Monday's closest approach is a span you could count on your fingers. That is not a knock on Farpoint or Mount Lemmon. Those observatories did exactly what they exist to do, and they did it well. It is a statement about the object. 2026 JH2 was simply not detectable until it was nearly here, and that sentence, not detectable until it was nearly here, is going to turn out to be the single most important sentence in this entire video, because it is not unique to this rock. It is the normal condition for an entire size class of objects, and we are going to spend the next part understanding exactly why. Sit with that. The headline says newly discovered. It does not really land until you understand what newly means here. It does not mean discovered last year and refined recently. It means discovered essentially now, right before arrival. And the thing is, there is no confirmed impact threat from this object. I want to be completely clear about that, because I'm not here to scare you about Monday. The current orbital models show 2026 JH2 passing and continuing on its way, out past us, back into the dark. Monday is a near miss, and near misses, in the cosmic sense, are routine. But the central uncomfortable fact of this whole event is the fact that has nothing to do with whether this particular rock hits us. It is this: a 50 to 100 foot asteroid was able to approach to within a quarter of the moon's distance, and our notice period was a handful of days. And if this rock had been on the trajectory that ends here, the warning would have been the same. the same few days, and we'll spend the rest of this video on what that few days is actually worth, because the answer is the part you're not ready to hear. Here is the question I want you holding on to, the one this entire video is built around. If the system that found 2026 JH2 is working exactly the way it was designed to work, and working as designed still means a 70-foot asteroid can reach a quarter of the moon's distance with only days of warning, then what honestly happens the day the next one of these is not a near miss? Keep that question in your mind. We are going to come back to it, again and again, and the answer is going to get more specific and less comfortable every time. Part 2. Working as designed. There is a phrase that gets used when something fails, and the phrase is, the system failed. And there is an instinct when you hear that an asteroid got within a quarter of the moon's distance and we only spotted it a few days out to reach for that phrase. Somebody dropped the ball, some telescope was pointed the wrong way, some agency was asleep. I need to take that instinct away from you, because it is wrong, and the truth is worse than the instinct. The system did not fail. The detection of 2026 JH2 days before closest approach is the system working. This is the designed, expected, normal performance of the global asteroid detection network for an object this size. Nobody made a mistake. This is just what the machine does, and once you understand why, the calm headline stops being calm. Let me explain how the catalogue actually works, because most people picture it completely wrong. Most people imagine that somewhere there is a master list, and on that list is every dangerous rock in the neighbourhood, with its orbit plotted and its arrival time marked, and the list is basically complete, and we are basically watching everything. That is not the situation, not even close. What actually exists is a catalogue of near-Earth objects that has been painstakingly assembled over decades, and it contains tens of thousands of asteroids, and it is a genuine achievement. But the completeness of that catalogue is not uniform. It drops off a cliff as the objects get smaller, and the reason is simple physics. A bigger asteroid is brighter, it reflects more sunlight, it is easier to catch. A smaller asteroid is fainter, dimmer, harder, and there are vastly more of the small ones than the big ones. So the catalogue is not one catalogue. It is really 3 different catalogues with 3 completely different levels of trust, sorted by size. At the top, the big ones. The objects a kilometre across and larger. These are the true civilization enders, the ones that would not just destroy a region but would alter the entire planet's climate, the dinosaur killer class. And here is the good news, and it is real good news, so take the win. For that class, the catalogue is believed to be more than 90% complete. We have found, by best estimate, more than 9 out of 10 of the objects big enough to end us. We have plotted their orbits. We know where they are and where they are going for a long time out. None of the known ones are coming for us. That is a genuine triumph of the surveys, decades of patient work, and it means the absolute worst case, the species-ending impact, is something we can say with real confidence is not on the books. Hold on to that, because the rest of this gets darker, and that piece stays true. The middle tier is where it starts to slip. These are the objects around 140 meters and larger, not planet killers. But this is the regional devastation class. An object in this range does not end civilization, but it could erase a city, or generate a tsunami that wipes a coastline, or flatten an area the size of a small country. NASA was given a goal, years ago, to catalogue at least 2/3 of this population, find 2/3 of the city killers, and that goal has not been met. The most recent figures from the planetary defence community put the fraction of these 140-metre plus objects that have actually been found at somewhere around 40%. 40%. Which means that for the class of object that could take out a metropolitan area, roughly 6 out of every 10 of them are right now unknown, not tracked, not plotted, not on any list, just out there, on their orbits, undiscovered, and the only way one of them enters the catalogue is if a survey telescope happens to catch it. And then there is the bottom tier, the one 2026 JH2 belongs to, the tens of meters class, the Chelyabinsk class, the Tunguska class. And for this size of object, the catalogue is not 40% complete, it is not 90% complete, it is radically, profoundly incomplete. We are talking about a few percent or less of the objects this size having ever been catalogued. The overwhelming majority of rocks in 2026 JH2's size range are simply unknown, until the moment they are close enough and bright enough to trip a survey telescope. And that moment, the moment they become detectable, is usually a matter of days before they arrive, sometimes a couple of weeks if the geometry is kind. Sometimes, and this is the part that should genuinely unsettle you, sometimes 0. Sometimes the warning time is nothing at all. I want to make sure the reason for that tiering really lands, because it is not arbitrary, it is the unavoidable consequence of two facts working against each other. The first fact is brightness. A larger object reflects more sunlight, so it is brighter, so it can be seen from farther away, which means it can be caught earlier and tracked longer. A smaller object reflects less, is dimmer, can only be seen when it is already close. The second fact is population. The small objects are not just a little more numerous than the large ones, they are vastly more numerous. There are a few large objects and there are an enormous number of small ones, so you have the worst possible combination. The objects that are hardest to see are also the ones there are the most of. The catalogue is most complete exactly where there is the least to find, and least complete exactly where there is the most to find. That is why the tiers exist. It is not that anyone decided to ignore the small rocks. It is that the small rocks are individually faint and collectively countless, and the survey telescopes, good as they are, can only ever catch the ones that drift close enough to cross the brightness threshold. The catalogue is not a map of what is out there. It is a map of what has been bright enough to notice, and it is worth being honest that this is not for lack of effort or for lack of talent. The asteroid survey programs are run by serious people using genuinely impressive instruments, wide-field telescopes built specifically for the job of scanning huge swathes of sky every night and feeding the images into detection software. Over the past couple of decades, those surveys have driven the discovery rate of near-Earth objects up dramatically. They are the reason the big object catalogue is as complete as it is. They are a quiet success story. But they are ground-based. They are finite in number. They can only watch the sky that is dark and above the horizon from where they sit, and they are fighting against the brightness and population problem I just described. They have been handed an enormous task and a real but limited set of tools, and the tiered catalogue, excellent at the top and nearly empty at the bottom, is the honest output of that situation. It is what doing this job well actually looks like right now. Which is the uncomfortable part. The tiered catalogue is not the surveys failing. It is the surveys succeeding at the task as it currently can be done. Because here is the blind spot, and it is not a metaphorical blind spot, it is a literal one. Our survey telescopes are on the ground, and they work at night, and they look out into the dark away from the sun. That is how telescopes work. You cannot see faint asteroids in the daytime sky any more than you can see faint stars in the daytime sky. The sun's glare drowns everything. So there is an entire region of space, the region between Earth and the sun, the sunward direction, that is effectively invisible to us from the ground. An asteroid approaching from that direction, coming at us out of the glare, is something our ground-based survey network cannot see, at all, until it has already passed into the night side, or until it is already in the atmosphere. And this is not hypothetical. This is exactly what happened at Chelyabinsk. I told you about the Chelyabinsk object in the last part, the 60-foot rock, the 1,500 injured, the broken glass across 6 cities. Here is the detail I held back. That object was detected by nobody. Not one telescope, not one survey, not one astronomer caught it before it entered the atmosphere over Russia. The warning time for Chelyabinsk was 0, and the reason was the blind spot. It came in from the direction of the sun, out of the daytime sky, and the first instrument to register its existence was 1,000 dashboard cameras and security cameras as it blazed overhead. That is not a story from the distant past. That is 2013. That is within the era of the modern surveys. An object the size of the one passing us on Monday hit the atmosphere over a populated city, and the entire planet's detection apparatus had nothing, because the rock came from the one direction we cannot look. And I want you to really feel the shape of that, because it reframes the whole flyby. We have a survey network that watches the night sky, and it works, and it is the reason we know about 2026 JH2 at all. But that network is, by its nature, watching half a sphere. It watches outward, into the dark, away from the sun. The other half, the half that contains the line between Earth and the sun, is simply not available to it. An object on an orbit that brings it at us from sunward is approaching down a corridor our telescopes cannot point into without being blinded. So when we talk about the catalogue being nearly empty for small objects, there is a second layer to it. It is not just that the small objects are faint, it is that even a small object that would be bright enough to catch is invisible to us if it happens to be coming from the sunward side. The blind spot is not a small gap at the edge of our coverage, it is an entire approach corridor. And the unsettling thing about Chelyabinsk is that it is not a freak story we tell to dramatise a remote possibility. It is the documented, recent, real example of an object using that exact corridor. It did not slip through a crack. It came down the one road we have no camera on. And it is worth saying plainly that there is nothing about the laws of orbital mechanics that makes the sunward corridor rare. Objects approach from sunward all the time. It is just that those are the ones we do not get to count, because we cannot see them, which means our sense of how often it happens is itself shaped by the blind spot. We are, in a real sense, estimating the frequency of a thing using an instrument that cannot detect the thing. So when I say the system is working as designed, this is what I mean. The design has a known, structural, physical limitation. We can only catch the objects that are bright enough, and far enough from the sun's glare, and well placed enough to show up in a night sky telescope. 2026 JH2 met those conditions, just barely, just in time, a few days out. Plenty of objects its size do not meet those conditions at all, and the catalogue reflects that. The catalogue is excellent at the top, shaky in the middle, and nearly empty at the bottom, and 2026 JH2 lives at the bottom. The few days of warning we got is not a fluke, and it is not a failure. It is the number. It is what the system produces for a rock this size. And the calm headline, "Newly discovered asteroid will safely pass Earth," is really saying something much less calm if you translate it honestly. It is saying the detection system caught one of the small ones in time to watch it go by, and that is the system at its best. Which brings the central question back, sharper now. If days of warning is the system working, the system at its best for a 70-foot rock, then the warning is not the problem we can fix by being more careful or more funded on the detection side alone. The detection side is doing roughly what the physics allows. The problem is what comes after the warning. The problem is the part nobody put in the headline. We found it. Good. Now what? And the honest answer to now what is the subject of the next part, and it is the answer that the phrase you're not ready to hear was pointing at all along. Part 3. Now what? Imagine the warning is real. Not a drill, not a near miss, the real thing. Some night this year or next year, a survey telescope catches a faint moving point that was not there before. The orbit gets worked out over the next few observations, and the answer comes back, and the answer is not, it misses. The answer is, it does not miss. There is an object and it is coming, and the warning time you have is the warning time these objects give you, which for something in the tens of meters class is days, and for something in the city-killing class might be longer if you are lucky enough to have caught it on an earlier pass, but might also be short. So the alert goes out. The detection worked. The system did its job. And now the only question that matters is the question this whole video has been walking toward. What can we actually do? And the honest answer, the one the calm headlines never get around to, is almost nothing. Right now, today, in the real world, there is no operational system that takes an asteroid warning and turns it into an asteroid deflection. There is no fleet of interceptors sitting on pads. There is no protocol with a button. There is no standing capability anywhere on Earth that converts a detection into an action on a timeline of weeks or even months. What we have is a single successful science experiment, and the gap between a successful science experiment and an operational planetary defense system is the entire subject of this part, because that gap is enormous, and that gap is the terrifying implication. Let me tell you what we do have, because it is genuinely impressive, and I do not want to undersell it. In 2021, NASA launched a mission called DART. The name stands for Double Asteroid Redirection Test, and the mission was exactly what it sounds like. The plan was to fly a spacecraft into an asteroid, on purpose, and see if hitting it would change its orbit. The target was carefully chosen. There is a near-Earth asteroid called Didymos, and Didymos has a small moon, a little moonlet orbiting it called Dimorphos. Dimorphos is roughly the size of a stadium, and in September of 2022, the DART spacecraft travelling at thousands of miles an hour slammed directly into Dimorphos. And it worked. The impact measurably changed Dimorphos's orbit around its parent asteroid. It shortened the time it takes the moonlet to go around. Not by a trivial, barely detectable amount either. The change was clear and significant and observable from Earth. DART proved something that had only ever been theory before that moment. It proved that a kinetic impactor, which is just a fancy way of saying a thing you crash into another thing, can actually change an asteroid's orbit. That is a real achievement. That is humanity, for the first time in the 4.5 billion year history of this planet getting hit by rocks, reaching out and altering the path of one on purpose. But now I have to tell you everything DART was not, because this is where the comfort runs out. DART was one test, one, against one specific, carefully selected, conveniently located object, chosen precisely because its setup made the result easy to measure. It was planned over a span of years, years of design, years of building, years of flight time. It was a demonstration under ideal, pre-arranged, take all the time you need conditions. It was the equivalent of proving, in a controlled experiment, that water can put out fire. That is a true and important thing to establish. But proving that water puts out fire is not the same as having a fire department. It is not the same as having trucks, and hoses, and crews, and a number you can call, and a response that arrives in minutes. DART proved the principle. Nothing has been built on top of the principle. There is no fire department. There is a single, brilliant, one-time demonstration that the physics works, and then there is a void where the operational capability should be. And I want to be specific about why the target was chosen the way it was, because the choice itself tells you how far we are from readiness. Dimorphos, the moonlet that DART hit, was not picked because it was a threat. It was picked because it was a measurement. It orbits its parent asteroid, and that orbit has a clean, regular timing, like the hand of a clock. So when you nudge the moonlet, you can watch the clock and see whether the hand sped up or slowed down. The whole experiment was designed around the fact that the result would be readable. That was the right call for a science test, but a real threat would not come pre-packaged for easy measurement. A real threat would be a single object on a path toward Earth, with no convenient orbiting partner to serve as a clock, and the question would not be, can we measure a change? The question would be, can we produce a large enough change, aimed precisely enough, with enough lead time to turn a hit into a miss? DART did not answer that question. DART answered a narrower, friendlier question, and answered it well, and that was the appropriate first step. But it was a first step, and there has not been a second step. And a first step with no second step is not a capability. It is a proof sitting on a shelf. There is also a quieter problem buried in here, and it is the problem of variety. Asteroids are not all the same kind of object. Some are solid rock, some are more like loosely bound piles of rubble, gravel held together weakly by their own faint gravity. Some are metal rich and dense, some are porous and fragile. And how an object responds to being hit, whether the nudge transfers cleanly into a change of orbit, or whether the impact just buries itself and throws up a spray of debris, depends heavily on which kind of object it is. DART hit one object, of one type. We learned something real from that one hit, but we did not learn how the other types respond, and a real defense system would need to work against whatever kind of object actually showed up, not just the kind we happen to test on. So even the proof we have is a proof about one case, and the space of cases is wide, and most of it is unexplored. That is not a reason to dismiss DART. DART was genuinely important. It is a reason to be honest that the distance between what DART showed and what an operational defense would require is not a short distance. It is most of the distance. And the void is not just a matter of, well, we have not gotten around to building the interceptors yet. The void is harder than that, because of the physics of deflection itself. Here is the thing about nudging an asteroid that makes it so unforgiving. You cannot stop an asteroid. You cannot blow it to a fine mist and have the problem disappear. That just turns one problem into 1,000 smaller problems on the same trajectory. What you can actually do, what DART actually did, is change its speed by a tiny amount. A nudge. And the way a tiny nudge turns into a miss is time. You change the asteroid's velocity by a hair, and then you let that hair compound, orbit after orbit, the tiny difference growing and growing, until what started as a hair's width of change has become the difference between hitting Earth and sliding past it. The nudge is small, the leverage is time, which means the entire strategy depends on having that time, on applying the nudge far enough in advance for it to add up. Now run that against the warning times we just talked about. Days for a tens of meters object, maybe longer for a bigger one, maybe not. The deflection strategy that we have proven works, the kinetic impactor, the nudge, is a strategy that needs years of lead time to be reliable, because it needs the nudge to compound, and the detection system for the small and medium objects frequently gives you days. There is a mismatch at the very centre of planetary defence. The one tool we have proven works needs a runway measured in years. The warning we typically get is measured in days to months. The tool and the warning do not fit together, and nobody is building the thing that would close that gap, because closing it would mean either a detection system good enough to find these objects years out, which is a massive undertaking that does not currently exist for the small classes, or a response system fast enough and powerful enough to do something meaningful with only weeks of notice, which is a different massive undertaking that also does not currently exist. People sometimes ask at this point, well, what about just blowing it up? If we cannot nudge it in time, why not destroy it? And the answer is that destruction is usually the worst option, not the best one, and it is worth understanding why. Because the intuition is so strong and so wrong. If you take a single incoming object on a collision path and you shatter it, you have not removed the threat. You have multiplied it. You now have a cloud of fragments, and that cloud is, on average, still on the same collision path, because breaking something apart does not change where the pieces are heading, it just changes how many pieces there are. Instead of one impact you can at least model and understand, you get a spread of smaller impacts across a wider area, and depending on the timing and the geometry, you may have turned a single localized event into a regional shotgun blast. There are narrow scenarios where disruption is the least bad choice, generally when the warning time is so short that no gentle method could possibly work, and the object is small enough that fragmentation genuinely reduces the harm, but those are edge cases, and they are edge cases precisely because in most situations breaking the rock makes the problem worse. The serious approaches, the kinetic impactor, and the slower gravitational methods where a spacecraft flies alongside an asteroid for a long time and lets its own faint gravity tug the asteroid onto a new path, all of them are about gently changing the object's course while it is still far away. All of them, again, need time. There is no method, anywhere in the serious planetary defense toolkit that works well with a short warning. The entire field is built on the assumption of lead time, and lead time is exactly the thing the detection system for small objects does not reliably give us. So the gap is not one gap, it is two gaps that compound each other. There is a detection gap, the small object catalogue is nearly empty, and the sunward corridor is invisible, so we frequently get short warning. And there is a response gap. The only proven tool needs long warning, and nothing operational has been built even around that. And the cruel part is the way the two gaps reinforce. If detection were good enough to find everything years out, the response gap would be survivable, because we would have time to improvise. If the response system were fast and powerful enough to act on weeks of notice, the detection gap would be survivable, because short warning would still be enough. But we have neither. We have short warning and a long lead time tool, and the space between them is where the whole problem lives. That space has a name, even if no agency calls it that. The name is, we found it, and there was nothing we could do. So let me give you the honest projection, not the scary movie version, the realistic version, which is somehow worse because it is plausible. If a city-threatening object were discovered tomorrow with a warning time of a few weeks or a few months, the response would not be a launch. The response would be a scramble. It would be the world's space agencies trying to improvise a mission from scratch, designing and building and launching a deflection attempt against a clock with no pre-built hardware, no rehearsed plan, no proven procedure for this specific situation. And the deflection physics, the part that needs time to let the nudge compound, would be working against them the entire way, getting less forgiving with every week that ticked off the clock. It is possible they would pull something together. Human beings can do remarkable things when the alternative is unthinkable, but possible is not the same as ready. And right now, on the question of readiness, the honest answer is that we are not. This is the implication the title was pointing at. Not that 2026 JH2 is going to hurt anyone, it is not. The implication is that the calm story we tell about these flybys, newly discovered, close, but safe, has a piece deliberately left out, and the missing piece is that the safe was luck, not capability. The trajectory missed us. We did not make it miss us. We could not have. And the next time the trajectory comes back, if it is one of the ones that does not miss, the few days of warning we will get is a few days to watch, not a few days to act. We have proven we can nudge a rock. We have not built anything that could nudge the rock that is actually coming. That is the gap. And the rest of this video is about why that gap is not a freak oversight, why it is not going to fix itself, and why the sky on Monday is going to be a little more crowded than just one rock. Part 4. The Wave. 2026. JH2 is not arriving alone, and that is the part of this story that turns it from a single flyby into something you really need to understand, because one rock passing close is routine, but what is happening this week is not just one rock. In the same stretch of days that 2026 JH2 makes its approach, the public asteroid tracking lists, the close approach tables that get assembled from JPL's data and republished on sites that monitor this stuff, have lit up with an unusual crowd of entries. Not one object inside the moon's orbit this week, around 8 of them. Let me put that in context, because 8 is a number that means nothing without a baseline. A single asteroid passing inside the Earth-Moon distance is common. It happens many times a year. It is, by itself, not news. What is less common, what is genuinely on the high end of what people who watch these lists closely tend to see, is 8 of them, clustered into a single week. Independent observers who track the close approach tables as a regular practice have flagged exactly this. One commentator who monitors these lists noted that he first started paying attention when 3 asteroids passed inside the Earth-Moon distance across just 4 days, and thought that alone was worth remarking on. And then, within roughly a week, the count of objects passing closer than 1 lunar distance had climbed to around 8. He described it as one of the densest weeks of sub-lunar distance flybys he had seen in all his time watching. So this is not me dramatising a normal week. The week itself is unusual, and the people whose habit it is to watch these tables are saying so. So what is in the wave? The objects in this cluster are all small near-Earth asteroids, the same general population 2026 JH2 belongs to, and they carry the same kind of designations that 2026J series of names, because they were mostly found recently in this same observing season. There is 2026 JK2, an object on the order of 80 feet across, around 26 meters, making its closest approach on May 15th at about 1.24 lunar distances, and notably it is moving fast, around 20.5 kilometers per second relative to Earth. There is a string of others, designations like JM2, JU1, JX1, JF2, JD1, JV1, JT, most of them passing within or just beyond 1 lunar distance, across roughly the span of May 14th through the 20th. And then there is 2026 JH2 itself, our Monday object, sitting right at the close end of that whole group, one of the nearest passes of the entire wave. 8 or so rocks, 1 week, all of them threading the same patch of near-Earth space. And I want to pause on those designations for a second, the J series, because the naming itself is quietly telling you something. The way these provisional names work, the year comes first, and then a pair of letters that encodes when in the year the object was found. That cluster of J letters means all of these objects were picked up in the same recent stretch of time. They were not sitting in the catalogue for years, tracked and understood. They were found, essentially now, in the run-up to their own flybys, the same way 2026 JH2 was. So the wave is not 8 objects we had been following. It is 8 objects we discovered on their way in. Every single one of them is its own small version of the same story, found late because late is what the system produces. The wave is not just a cluster of flybys, it is a cluster of short-notice discoveries, 8 of them stacked into 1 week, and that makes it less a curiosity and more a demonstration. It is the detection gap, happening 8 times in a row in front of us, in real time. It is also worth being clear-eyed about the sizes in the wave, because a couple of these objects are not trivial. 2026 JK2 at around 26 meters is comparable in scale to the Chelyabinsk object, and it is moving fast, which as we discussed means it carries proportionally more energy for its size. 2026 JH2 itself, at 50 to 100 feet, is in the same conversation. These are not boulders. These are not the pebble-sized debris that burns up harmlessly as shooting stars every night. Several of the objects in this week's wave are large enough that, on a different trajectory, they would be a serious event for whoever was underneath. None of them is on that trajectory. I want to keep saying that because it is true and it matters. None of these 8 is going to hit us. But the sizes are a reminder that the wave is not a cute astronomical footnote. It is 8 objects, several of them genuinely consequential in size, that we did not know about until they were nearly here, passing through our neighbourhood in a single week. The harmlessness of this particular week is a fact about these particular trajectories. It is not a fact about the system that found them. Now here is where it gets genuinely interesting, and where you need to picture something, so let me build the picture for you. There is a tool, a public one, the NASA Orbit Visualizer, that lets you take any of these objects and plot its orbit around the Sun, the whole ellipse, the entire loop. And when you take the 8 objects of this week's wave and plot all their orbits together, on the same diagram, something jumps out. Out at the far points of their orbits, away from us, the orbits look nothing alike. They have different shapes. Some are stretched into long ellipses, some are rounder. They have different sizes, different orbital periods. The time it takes each one to go around the Sun is different. They are tilted at different angles to the flat plane that the planets mostly travel in. By every measure, out there in the far reaches, these are 8 unrelated objects on 8 unrelated paths. But then you follow the orbits inward, toward us, and they converge. The paths draw together. They crowd into a tight region, and that tight region is right at Earth's orbital path. 8 orbits that look completely different out there, all bending in toward the same narrow zone right where we live. And it is not just that they cross the same zone, they cross it close together in time. Several of the objects in this wave pass within a day or two of each other, in loosely associated pairs, one and then another right behind it, like cars going through the same intersection in a cluster, rather than spread evenly through the day. And there is one more pattern in the data, a subtle one, but it matters, and we will come back to it hard in the next part. The objects in this group that pass closest to Earth also tend to be the ones with the lower relative velocities. They are moving more slowly with respect to us. And the objects that pass at a bit greater distance, like 2026 JK2 with its high speed and its steep orbital tilt, tend to be the faster, more steeply inclined ones. The closest ones are the slow ones. Tuck that away. It is a clue, and it is a clue about something much bigger than this week. Let me make sure that clue is vivid before we move on, because it is going to be the hinge of the entire next part. Picture 2 objects approaching the same crowded region of space. One of them is moving fast relative to Earth, and its orbit is steeply tilted, cutting across the plane of the planets at a sharp angle. The other is moving slowly relative to Earth, and its orbit lies nearly flat in the plane, nearly parallel to Earth's own path. Which one is more likely to come truly close? It is the slow, flat one. The fast, steeply tilted object is crossing through quickly and at an angle. It punches through the region and is gone. The slow, flat object lingers in the same neighbourhood as Earth, travelling almost alongside us, and that is the object that can ease in close. And when you look at this week's wave, that is exactly the sorting you see. The nearest passes, 2026 JH2 among them, are the slower, flatter objects. The more distant passes are the faster, more tilted ones. That is not random. That sorting, slow and flat, ends up close, fast and tilted stays farther out, is the visible signature of a real physical process, and in the next part I am going to show you that the process has a name, and that it is the same process that built the planet you are standing on. The wave is not just 8 rocks, the wave is 8 rocks arranged in a pattern, and the pattern is a fingerprint. Now, I have to be careful here, and I am going to be, because the honest version of this story includes a serious objection, and I am not going to hide it from you. The objection goes like this. Of course these orbits converge near Earth. We only know these objects exist because they came near Earth. We detected them precisely because they swung through our neighbourhood and got bright enough and close enough to catch. So is it really meaningful that their orbits all converge on us? Or is that just the obvious consequence of how we found them in the first place? If you only ever notice the cars that drive past your house, you should not be amazed that all the cars you have noticed drove past your house. That is a real objection. It is the strongest counter-argument to the whole wave being significant, and I want you to hold it in your mind because we're going to deal with it directly and fairly a little later in the section on the alternative explanations. The short version, the version I will expand later, is that the objection is partly right and partly incomplete. It is real, but it does not explain everything, and in particular, it does not explain why this specific week is so crowded. But set the objection aside for one moment, because whether the wave is partly an artifact of how we look, or partly a real concentration of objects, it does one thing that is not in dispute. It makes the detection problem from the last 3 parts concrete. It takes it out of the abstract. Because here is what the wave really is, stripped down. It is 8 rocks we could see. 8 objects that happen to be bright enough and well placed enough and far enough from the sun's glare to show up in our telescopes this week. The wave is the visible portion, and every single thing we said about the catalogue being nearly empty for objects this size, every single thing we said about the sunward blind spot, every single thing we said about Chelyabinsk coming in with 0 warning, all of that is still true underneath this wave. The 8 we are tracking are not the 8 that exist, they are the 8 that were catchable, and if 8 catchable ones came through in a single week, the honest question, the one that connects this whole part back to the spine of the video, is not how worried should I be about these 8. None of these 8 is going to hit us. The honest question is, if this is the visible portion, what is the size of the portion we cannot see, and what would our few days of warning be worth against an object pulled from that invisible half? The wave does not change the answer to that question. The wave just makes it impossible to keep treating the question as abstract. Part 5. How the solar system builds things. I want to take you away from the fear for a few minutes, because there is something genuinely beautiful buried inside this story, and understanding it will actually change how you see that convergence we just talked about. The 8 orbits bending in toward Earth's path are not just a coincidence to be nervous about. They are a small, live, present-day example of one of the deepest processes in the entire solar system. The same process that built the planet you are standing on. And once you see it, the wave stops looking like an omen and starts looking like a window. So let me ask the question that planetary scientists have been chewing on for a very long time. How did the planets form at all? You have a young star, and around it a vast, thin, spread-out cloud of gas and dust, and somehow, over time, that diffuse smear of material becomes 8 distinct planets, neatly spaced, each one a compact ball orbiting in an orderly flat plane. How? The intuitive answer, the one you probably half remember from school, is gravity. Gravity pulled it together. And gravity is part of it, gravity is real and gravity matters. But if you actually sit down and run the numbers on a diffuse cloud of gas just collapsing under its own weight, you run into trouble fast. Gravity is, by a wide margin, the weakest of the fundamental forces. A thin, spread-out cloud does not obviously have enough self-attraction to haul itself all the way down into solid planets. And pure gravitational collapse does not naturally explain the other things we see. The orderly spacing of the planets, the way their densities differ, the way the whole system ended up flat and organised rather than a chaotic swarm. The simple story has holes in it. It has had holes in it for a long time. So there is another idea, an older one, associated with the Swedish physicist Hannes Alfvén and others who worked on what is sometimes called plasma cosmology and accretion theory. And this idea offers a different route, and it is the route that explains the convergence you're looking at this week. The idea is about what happens when you have an enormous number of small bodies, particles, grains, pebbles, rocks, all sharing a region of space, all on their own orbits around a central mass. Those objects do not just sit in their orbits forever, perfectly undisturbed. They interact. Sometimes that is an actual collision, 2 of them physically meeting. Sometimes it is just a gravitational nudge as they pass close, and there is a common assumption about what happens when objects meet in space. The assumption is that they bounce, elastically, like billiard balls, and maybe shatter, flinging fragments outward. And that does happen, but it is not the dominant outcome over long time scales. Over long time scales, the more consequential kind of interaction is the inelastic one, the kind that does not bounce cleanly, the kind that bleeds energy out of the system. And here is the key thing, the thing that makes the whole picture work. Every time you have one of those inelastic energy-bleeding interactions, it tends to make the orbits of the objects involved more similar to each other. 3 specific ways. First, the orbits get less eccentric, which means they get less stretched out, more circular. Second, the orbits get less inclined, which means they flatten, they settle toward a common plane. And third, the relative velocities drop, the objects start moving more slowly with respect to one another. less stretched, flatter, slower relative to each other. Interaction after interaction, over enormous spans of time, a population of objects that started out chaotic on every kind of orbit gets herded statistically toward orbits that are rounder, flatter, and gentler relative to their neighbours. Now hold that result up against the clue I asked you to tuck away in the last part. I told you that in this week's wave, the objects that came closest to Earth were the slow, flat ones, and the objects that stayed farther out were the fast, steeply tilted ones. Look at what the herding process predicts. It predicts that objects which have undergone more of these inelastic interactions will be the ones with lower eccentricity, lower inclination, and lower relative velocity. Rounder, flatter, slower. And those are precisely the properties that let an object ease in close to Earth rather than punching through at a sharp angle. So the sorting you see in the wave, slow and flat, ends up near, fast and tilted stays far, is not a coincidence, and it is not noise. It is what you would expect to see if the objects in the wave are at different stages of exactly this convergence process. The ones that came closest are, in a sense, further along the journey. They have had more of their chaotic, energetic orbit ground down toward the gentle, flat, slow state that the process drives everything toward. The wave is not just 8 rocks near Earth. It is 8 rocks caught at visibly different points along the same road, and the road leads toward convergence. That is what I meant when I said the pattern is a fingerprint. The fingerprint is the process showing its hand. It is worth pausing on why inelastic, energy-losing interactions are the ones that dominate over the long run, because the billiard ball intuition is so stubborn. When two small bodies in space encounter each other, the encounter is almost never a clean elastic bounce. Real rocks are not perfectly rigid spheres. They crush slightly, they grind, they may shed material, they radiate away a little heat. Every one of those is a channel for energy to leave the encounter. And critically, the energy that gets lost is the energy of relative motion, the energy that was keeping the two objects on different paths. Lose that, and the two paths drift toward each other. Now, on any single encounter, the effect is tiny, almost nothing. But the solar system does not run on single encounters. It runs on enormous numbers of encounters over enormous spans of time, and a tiny effect applied a near infinite number of times is not a tiny effect anymore. It is a current. It is a direction, and the direction always points the same way, toward less relative energy, toward convergence. That is why the process has a direction at all. Fragmentation, the shattering, scatters things and adds relative energy, and it does happen, but it is the swimming against the current. The convergence is the current itself, and once a group of objects is moving slowly relative to each other, sharing nearly the same circular orbit in nearly the same plane, something can finally happen that could not happen before. They can come together and stick instead of shattering. Gentle accretion becomes possible, slow things touching. Slow things do not blow apart, they merge, and now you have your root. Infalling material, gas and dust, ionized and shaped by magnetic fields and the rotation of the system, condensing first into grains, grains accumulating into pebbles, pebbles into meteoroid-sized chunks, those into asteroids. Asteroids, through this same convergence and gentling process, drawing together into larger bodies called planetesimals, and planetesimals in the denser streams of material running away with it, growing fast, sweeping up everything in their lane, becoming planets. The whole hierarchy, dust to world, and the engine of it is this slow, statistical herding of orbits towards sameness, followed by gentle merger. Now, does this picture have evidence behind it, or is it just a pretty story? It has evidence, and the best piece of evidence is sitting in our own solar system, in the asteroid belt. There is a popular image of the asteroid belt as the wreckage of a planet that exploded, a world that used to orbit between Mars and Jupiter, and somehow blew apart, leaving a ring of debris. It is a dramatic image. It is also almost certainly wrong, and the reasons it is wrong tell you something. For one, the entire asteroid belt, all of it added together, only amounts to about 1% of the mass of Earth. That is not the leftovers of a planet. That is barely the leftovers of a small moon. For another, if you measure how the belt's material is distributed across its orbital zone and compare it to the equivalent figure for the inner planets or for Jupiter, the belt's density of material is roughly an order of magnitude lower. An exploded planet would not leave a signature that different from its neighbours, and flinging the missing mass clear out of the solar system entirely would take a staggering amount of energy because the sun's gravity is a deep, deep well to climb out of. The exploded planet idea does not fit the numbers, but the accretion picture fits them perfectly. Because what the asteroid belt actually looks like is not an explosion. It looks like an accretion process that started and then stalled. It looks like a place where the herding and the merging began but never finished, probably because Jupiter's enormous gravity nearby kept stirring the pot, kept the relative velocities too high, kept knocking the orbits around so they never fully gentled, and the fingerprint of a stalled accretion is right there in the belt structure. The single dwarf planet Ceres, just one object, contains roughly a third of the entire belt's mass. Add the next three largest bodies, and you have captured the large majority of all the mass in the belt. Everything else, the countless thousands of smaller asteroids, all of them put together, is just a small remainder. That is not the signature of an explosion, which would scatter mass everywhere. That is the signature of a few winners, a few bodies that got far enough along in the convergence and merging process to start sweeping up their neighbours, growing at everyone else's expense, while the process froze before any of them could become a true planet. Ceres is what a planet looks like when it got interrupted halfway, and the belt is not the only place this pattern shows up. The composition of the asteroids is its own argument against the exploded planet idea, because the belt is not made of one kind of material the way the fragments of a single shattered world would be. It contains a real variety of compositions, rocky bodies, metal-rich bodies, dark carbon-rich bodies, and there is good reason to think it also holds objects that did not even form there, bodies nudged inward from the cold outer solar system, perhaps even the occasional captured visitor from interstellar space. A shattered planet would be relatively uniform, the pieces of one thing. The belt is a mixture, a collection of objects with different origins and different histories that happen to share a region of space. That is what an accretion zone looks like, a place where material from many sources is slowly being gathered and worked, not a place where one object came apart. Everywhere you look in the belt, the evidence points the same way, not a wreck, a construction site where the construction stalled. You can even see the same logic operating in places far beyond the belt. Out past Neptune, in the cold outer reaches of the solar system, there is another vast population of icy bodies, dwarf planets and comets and countless smaller objects, and that region too looks like a place where accretion ran part way and then thinned out, where a few larger bodies gathered up some of the material, but the process never completed into full planets. The solar system, looked at this way, is not a finished static thing with a few leftover crumbs. It is a process caught at a moment. Most of the inner solar system finished its accretion long ago. The material in those lanes got gathered up into the planets we know. The belt and the outer regions are the lanes where the process stalled, where you can still see the intermediate stages, the gathered winners, and the UN-gathered remainder frozen in place like a film paused partway through. And the near-Earth asteroids, the population 2026 JH2 belongs to, are objects that have been knocked out of those stalled regions and sent wandering on orbits that now cross ours. They are pieces of the unfinished work drifting through a lane where the work did finish, the lane that became Earth. So now bring it back to this week. Bring it back to 2026 JH2 and the wave. That cluster of near-Earth objects, their orbits bending in to converge on Earth's path, is a small, present-day, observable example of the exact same dynamics. Not a planet forming, I want to be clear. I am not telling you these 8 rocks are about to merge into a new world. The point is the opposite of that, and it is both more reassuring and more sobering at the same time. The point is that orbital convergence near a massive body is not strange. It is not an omen. It is not a sign that something is wrong. It is just how this solar system has always worked, at every scale, from dust grains to planets. Earth sits in its orbital lane. Earth's gravity, like the gravity of every massive body, focuses and shepherds the population of small objects that pass nearby. Those objects interact, and their orbits, statistically over time, are herded toward convergence. And we know exactly what the long-term outcome of orbital convergence near a massive body is because we are standing on it. The outcome is accretion. The outcome is impacts. Earth has been accreting this material across its entire 4.5 billion year existence. The craters on the surface are the visible record of it. and the far greater number of craters that erosion and oceans and the slow churn of plate tectonics have erased are the invisible record of it. That is the terrifying implication said plainly, and notice that it has nothing to do with this week being special. The flyby wave is not a warning that the sky is suddenly falling. The flyby wave is a reminder that the process never stopped. It has been running the entire time. Earth is still inside it. The rocks still converge, because convergence is the rule, not the exception. And the only variable in the entire equation that human beings get any say over, the only lever we have a hand on, is whether we can see the next one coming and whether we can do anything when we do. The solar system's part of this is fixed. It has been fixed for billions of years, and it will keep running for billions more. Our part, the seeing and the doing, is the only part that is up to us. And we have already spent 3 parts of this video establishing exactly how thin the seeing is and exactly how empty the doing is. The accretion never ends. The question is only ever whether we are ready for our turn in it. Part 6. The things we already know. It can do, and the stories we tell to feel better. Before we go any further into what we cannot do, I want to ground this in what these objects actually do when they arrive, because it is easy to talk about tens of meters and lunar distances and lose the thread of what is physically at stake. So let me give you 2 real events, 2 rocks that did not miss, and let them set the scale. The first one you have already met in this video, Chelyabinsk, February 2013, an object roughly 60 feet across, squarely inside the size range of the asteroid passing us Monday. It came in over the southern Ural region of Russia, and it did not strike the ground. It detonated in the air, an airburst, at altitude, and that airburst released energy estimated in the range of 400 to 500 kilotons of explosive force. To give that a reference, that is many times the energy of the bomb dropped on Hiroshima. The shock wave from that airburst spread out and reached the ground across a wide area, and it blew out windows across 6 cities, and it injured around 1,500 people. And remember the mechanism, because the mechanism is the lesson. The injuries were not from the rock. The rock never touched anyone. The injuries were from glass, from people who saw the brilliant streak of light, brighter than the sun for a moment, and did the most natural thing a human being can do. They went to the window to look, and they were standing at the window when the shockwave arrived a couple of minutes later and turned the glass into 1,000 flying blades. That is a 60-foot object. That is the lower middle of the range we're discussing, and it came, as I told you, from the sunward blind spot, detected by no one, 0 warning. The second event is older and bigger, Tunguska, June 1908, in remote Siberia. The object there was larger than Chelyabinsk, though by best estimates not as much larger as people tend to assume, somewhere in the range of 160 to 200 feet across, and it too exploded in the air rather than cratering. But the energy of the Tunguska airburst is estimated in the range of several megatons up to over 10 megatons, and it flattened an estimated 830 square miles of forest. 830 square miles. Trees knocked down like matchsticks, all pointing away from the blast, across an area larger than many major cities and their entire surrounding metropolitan regions. The only reason Tunguska is a scientific curiosity rather than one of the worst disasters in human history is that it happened over an almost completely unpopulated stretch of Siberian wilderness. Put that same object over a city, and the conversation is very different. Tunguska is the upper end of what the small body population can do without even being in the regional devastation class. It is what a couple hundred feet of rock does, and I want to draw out the lesson that sits underneath both of these events, because it is the same lesson and it is easy to miss. Neither Chelyabinsk nor Tunguska cratered the ground. Both of them released their energy in the air as an airburst, and a lot of people hear that and relax a little, as if an airburst is the gentle version. It is not the gentle version. The airburst is the mechanism of the damage. When an object this size comes screaming into the atmosphere, the air in front of it cannot get out of the way fast enough. It compresses violently, and the object essentially detonates from the stress and the heat, converting its motion into a sudden, enormous release of energy high above the surface. And that release propagates downward and outward as a shock wave and a pulse of heat. Chelyabinsk's broken glass across 6 cities was the shock wave. Tunguska's 830 square miles of flattened forest was the shock wave. The object does not need to touch the ground to do catastrophic damage to the ground. It just needs to arrive. So when you hear about some future object that it would probably airburst rather than impact, do not file that under good news. File it under, this is the form the damage takes. And then remember that the object passing us on Monday is in Chelyabinsk's size class, and the city killer objects we have only catalogued about 40% of are well above Tunguska's, and ask yourself how comfortable the phrase probably an airburst actually makes you. There is also a geographic accident hiding in both stories that is worth naming, because it is the thing we have actually been relying on, whether we admit it or not. Chelyabinsk happened over a city and hurt 1,500 people, but it could have been far worse. The object came in at a shallow angle that spread its energy out rather than concentrating it. Tunguska was a multi-megaton blast that flattened an area the size of a metropolis, and the death toll was effectively nil, purely because of where it landed, empty Siberian forest. In both cases, the thing that determined whether we are talking about a tragedy or a footnote was not our detection system, and it was not our response system, because we had neither working in those moments. It was luck. It was geography. It was where on a mostly empty planet the rock happened to come down, and that is the uncomfortable foundation under the reassuring statistics. When people say impacts of a certain size only happen every few decades or every few centuries, that framing quietly assumes the luck holds, assumes the next one also lands in an ocean or a desert or a forest. Most of the planet's surface is unpopulated, so most of the time the luck does hold. But planning around the luck holding is not a plan. It is just the absence of one, dressed up in a frequency statistic. So that is the scale. 2026 JH2, 50 to 100 feet, lives between Rutin and Chelyabinsk. The 140-meter class, the city killers that we have only catalogued about 40% of, lives well above Tunguska. These are not abstractions. These are windows and forests, and in the wrong place, much worse. Hold that scale, because it is the thing that makes the next subject matter, and the next subject is the stories people tell to make all of this feel more manageable, or more meaningful than it is. Because whenever a story like this one circulates, an asteroid wave, a close flyby, a warning, it does not travel alone. It travels with a set of alternative framings, and I think it is worth walking through them honestly, because some of them contain a real kernel, and the ones that do not still deserve a respectful, clear-eyed answer rather than a sneer. This channel does not promote these framings as fact, but it also does not pretend the impulse behind them is stupid, because it usually is not. The impulse is pattern recognition, and pattern recognition is one of the best things the human mind does. It just needs discipline. The first alternative framing is the strongest, and it is barely a conspiracy at all. It is really a scientific objection, and I promised you back in the wave section that I would deal with it fairly, so here it is. The objection is, this wave is just observer bias. We only found these 8 objects because they came near Earth. The convergence of their orbits on Earth's path is not a discovery, it is a tautology. It is built into the fact that proximity to Earth is the thing that made them detectable in the first place. And I want to say clearly that objection is partly correct, and anyone who dismisses it is not being honest with you. Observational selection absolutely does inflate the apparent convergence. If the only rocks you can see are the ones that come close, then naturally every rock you have seen comes close. That is real, and it has to be subtracted out before you get excited. But here is where the objection is incomplete. Subtracting out the selection effect does not make the whole thing vanish. For one, it does not explain the timing density, why this specific week is so much more crowded than a typical week, since selection bias is roughly constant week to week and should not produce a sudden cluster. And for two, there is genuine, mainstream, well-established physics, by which small bodies really do group together in ways that are not illusions, the gravitational focusing by Earth and the other planets, the orbital resonances, the slow dynamical clustering we spent the entire last part describing. So the honest and complete answer is this. The convergence is real as an observation. It is partly an artifact of how we look, and it is partly a genuine window onto real dynamics, and teasing apart how much is artifact and how much is real is not a settled question. It is an active research question. That is the intellectually honest position, and it is more interesting than either the breathless version or the dismissive version. The second framing is bigger, and you will see it attached to weeks like this one. It is the idea that the asteroid wave is connected to everything else happening to Earth right now, that the rocks and an incoming stream of fast solar wind from a hole in the sun's corona that is expected to spark a geomagnetic storm in the next few days, and the current alignment of Mercury and the Sun and Earth, and a run of volcanic and seismic activity are all part of one thing, one convergence of energies, one meaningful pattern. And I understand the appeal of this completely. The human mind hates coincidence. When several notable things happen at once, every instinct we have says, these must be connected, there must be a common cause. But this is exactly where the discipline has to come in, because the honest answer is that these are independent systems that happen to be active at the same time. The asteroid flybys are governed by orbital mechanics, by gravity and momentum, laws worked out centuries ago, and those laws have nothing to say about solar wind. The geomagnetic storm is driven by charged particles streaming off the Sun, and those particles have nothing to do with where a rock is in its orbit. The planetary alignment is a real geometric event. The planets really do line up, but the gravitational and tidal influence of a small distant planet like Mercury on Earth, or on a near-Earth asteroid, is many, many orders of magnitude too weak to be organising asteroid flybys or setting off earthquakes. The numbers are not close, they are not even in the same universe. And on the specific question of whether solar activity triggers earthquakes, which is a piece of this framing that comes up a lot, the peer-reviewed work that has actually looked for that link finds, at most, weak statistical correlations and never a deterministic trigger, and the energy budget argument settles it. The elastic strain energy released in a major earthquake dwarfs any plausible energy that space weather could couple into the ground, again by a wide margin. So the simultaneity is real. Several things are genuinely happening at once, but simultaneous is not the same as connected. Independent systems overlap in time constantly. That is just what it looks like to live on a planet with a lot going on. The pattern recognition instinct fires, and the discipline's job is to check whether there is actually a mechanism, and here there is not. And let me put a number on the tidal point, because I think numbers are the only thing that really kills this one, since the appeal is so emotional. The strength of a tidal pull, the kind of stretching influence one body exerts on another, falls off extraordinarily fast with distance. It drops with the cube of how far away the thing is. Double the distance and the tidal effect is not half, it is an eighth. The moon raises real tides on Earth because it is genuinely close and we feel it. The sun raises a smaller but real tide because it is so enormously massive that even at its distance the effect is meaningful. But a small planet like Mercury, tens of millions of miles away on its closest approach to us, exerts a tidal influence on Earth that is so far below the moon's, so far below even the everyday variation in the moon's own pull as it moves through its orbit, that it simply cannot be the lever that organises anything. The same is true in reverse for its influence on a near-Earth asteroid. When an alignment happens, the geometry is real. The planets really are in a line. But a line is just a line. It is a viewing arrangement, not a force. The forces involved did not spike because the dots got arranged. The dots getting arranged is something we notice. It is not something the asteroids feel. And I think that distinction between what we notice and what the objects actually experience is the whole key to handling this framing with both honesty and respect. The instinct to see the alignment as meaningful is the same good instinct that does real science. The instinct to look for structure. It just has to be paired with the discipline of checking whether the structure has a force behind it, and here, when you run the numbers, it does not. The third framing is the darkest one, and it is the idea that somebody knows about a genuinely dangerous object and is hiding it, or that the late discovery of 2026 JH2 is itself suspicious, evidence of a cover-up. And the answer to this one is structural, and I think it is actually reassuring once you see it. The detection of 2026 JH2 came from independent observatories in different states, and the observation was published into a public data system that anyone can look at. The close approach tables are open. They are republished by multiple outlets. Amateur astronomers and professional astronomers all over the world, in many countries, in rival institutions, track these objects independently and constantly. A real concealment of a real threat would require near impossible coordination across all of those competing, independent international actors, all of them agreeing to stay silent, none of them breaking ranks, in a field where being the one who spots the important thing is the entire professional reward structure. It does not hold together, and the late discovery is not evidence of a cover-up. The late discovery is evidence of exactly the capability gap this entire video is about. The boring explanation that the survey system is simply not complete for small objects, that we found it late because late is what the system produces, is both true and far more useful than the conspiratorial one, because the boring explanation points at something we could actually fix. The cover-up explanation points at nothing. It just makes you feel watched. The real story makes you ask for better telescopes. And the fourth framing is the one about deflection, and it comes in two versions. The cynical version says, since we cannot do anything about an impact anyway, why even tell the public? Awareness is pointless, ignorance is bliss. And the conspiratorial version says, the technology to deflect these things secretly exists and is being withheld. Let me take both plainly. On the secret technology, there is no evidence of a hidden deflection capability, and DART, the mission we discussed, is the actual public state-of-the-art. And the actual public state-of-the-art is one successful test with nothing operational built on top of it. The real situation, a proven concept and no system, is concerning enough on its own. You do not need to invent a hidden one. And on the cynical version, the idea that awareness is pointless, I want to push back on that hard because it is exactly backwards. Awareness is the opposite of pointless. Detection is the one part of planetary defense that genuinely works and is genuinely improving. The reason to care, the reason to pay attention to a Monday afternoon flyby, is that public attention is what funds the surveys, and the surveys are the part that is succeeding. Ignorance is not bliss. Ignorance is what keeps the budget flat. The case for funding the seeing harder, and for finally building the doing, is made precisely by events like this one, and it is only made if people are actually paying attention. So the cynical framing does not just give up, it gives up the one thing that is working. So those are the stories. And the through line, the thing that ties this whole part back to the spine of the video, is that the most truthful account of 2026 JH2 is also the least dramatic one, and it is still the most unsettling one. There is no hidden hand, there is no convergence of energies, there is no cover-up. There is just a real rock found late because late is what the system produces, passing close, this time safely. And the scale of what these objects do, Chelyabinsk's broken glass, Tunguska's flattened forest, is real, and it is the reason the boring truth is not actually comforting. The boring truth is that we are watching the sky with an instrument that has a known blind spot, and standing behind it with no fire department. That is not a conspiracy. That is just where we are. And it is worse than a conspiracy because a conspiracy could be exposed and fixed by exposure. This can only be fixed by building something, and so far, we have not. Part 7. A few days to watch. Let me build the scenario all the way out now because we have assembled every piece of it, and it is time to put them together and look at the whole thing honestly. This is not a disaster movie. I'm not going to give you a countdown clock and a square-jawed hero. I'm going to give you the realistic version, the version that follows from everything in this video, and the realistic version is unsettling precisely because there is nothing exaggerated in it. Some night, this year, next year, a survey telescope, one of the ones quietly scanning the dark, catches a faint moving point of light. It was not there the night before. Over the next few observations, over the next night or two, enough data comes in to work out the orbit. And the orbit gets computed and the answer comes back. And this time the answer is not, it misses. The answer is, it intersects. There is an object, and it is in the size class that matters, and its path and Earth's path are going to occupy the same point at the same time. The detection has worked, the system has done its job, the telescope caught it, the math is solid, and now you're standing inside the exact situation this whole video has been walking toward, and the warning time you're holding is the warning time these objects give you. For something in the tens of meters class, that is days. For something larger, the city killer class, it might be longer if you were lucky and caught it on a previous pass years ago, or it might be months, or it might also be short, and the alert goes out. And the question, the only question, is the one we asked back in part 3. What can we actually do? And we have spent this video answering that, so let me assemble the answer in full. We have one proven tool, the kinetic impactor, the nudge. DART showed it works, but the kinetic impactor is a tool with a specific requirement, and the requirement is time, because the way the nudge works is by being applied early enough that a tiny change in velocity compounds orbit after orbit into a large change in position, into the difference between a hit and a miss. The nudge is small, time is the multiplier. Take away the time, and the nudge is just a nudge. It does not move the rock far enough. So the tool we have proven works needs years of runway to be reliable. And the warning, for the objects we are most likely to be surprised by, is days to months. The tool and the warning do not fit. That is the mismatch at the dead center of planetary defense, and it does not go away by wishing at it. So what actually happens in the realistic scenario is not a launch. There is no interceptor on a pad. There is no rehearsed procedure for this specific object on this specific timeline. What happens is a scramble. The world's space agencies, which on a good day do not coordinate quickly, would be trying to improvise a deflection mission from nothing against a clock, designing and building and launching hardware that does not currently exist for a situation that was never pre-planned. And every week that passed during that scramble would make the deflection physics less forgiving, because every week subtracted is leverage subtracted. Time for the nudge to compound that you no longer have. Could humanity pull something together? Maybe. People can do extraordinary things when the alternative is unthinkable, and I do not want to be entirely fatalistic, because the base capability of our species to focus when it absolutely must is real. But maybe is not a plan. Possible is not the same as ready. And on the specific, narrow, unsentimental question of whether we are ready, today, the honest answer is no. And I want to walk through why the scramble is so much harder than people imagine. Because it is not just a matter of urgency. It is a matter of lead times that cannot be compressed no matter how motivated everyone is. Building a spacecraft, even a simple one, is not a thing you can do in a few weeks. There is design, there is the sourcing of components, there is assembly, there is testing. Because a spacecraft that fails on the way to its target is worse than no spacecraft at all. It is a wasted launch and lost time. Then there is the launch itself, which has to be scheduled, and the launch window, the specific stretch of time when the geometry between Earth and the target actually allows a spacecraft to get there, may not be conveniently open. And then, even after launch, there is the travel time, because the target is far away and spacecraft do not move instantly. They take months, sometimes longer, to cross interplanetary distances. So even in the most motivated, best funded, everyone pulling together version of the scramble, you are stacking design time plus build time plus test time plus a launch window plus travel time, and all of that is being subtracted from a warning window that, for these objects, started out measured in days to months. The math frequently does not close. It is not that the scramble fails because people are not trying. It is that the scramble fails because the clock was already shorter than the irreducible time it takes to build and fly the thing, and no amount of effort shortens the irreducible part. This is the entire argument for why the work has to be done in advance, before there is a specific rock with a specific date. The reason you want hardware designed and tested and understood ahead of time, the reason you want rehearsed procedures and pre-planned mission profiles, is that all of that work is the work that cannot be compressed. If it is done in advance, then when the real warning comes, the scramble is only the launch and the flight, not the launch and the flight, plus the entire process of inventing the response from scratch. That is the difference between a fire department and a brilliant theory about water. The fire department's value is not that it knows something the theory does not. The fire department's value is that the trucks already exist, the crews are already trained, and the response is measured in minutes, because everything that could be done in advance was done in advance. Planetary defense right now has the theory and not the department, and the scramble scenario is just the detailed picture of what it looks like to face a fire with a theory. I want to bring in one more object here, by way of contrast, because it shows you the difference between the situation we are usually in and the situation we would want to be in. The object is called Apophis. It is a near-Earth asteroid, but it is in a completely different size class from 2026 JH2. It is several hundred meters across. It is a genuine regional threat-sized object. And Apophis is going to make a very close, very well-publicized pass by Earth in 2029. Now here is the contrast. Apophis is not a surprise. We have known about Apophis for years. We have tracked it. We have refined its orbit over many observations. We have done the math over and over, and the current calculation says it passes safely in 2029. No impact. And because we have known about it for years, if the math had come back differently, we would have had years, the runway that the kinetic impactor actually needs, Apophis is what it looks like when the system gets a long lead time, and notice what made that long lead time possible. Apophis is big enough to catch early, big enough to be in the part of the catalogue that is reasonably complete. The long warning came from the size. 2026 JH2 is small enough to live in the part of the catalogue that is nearly empty, small enough that the warning was days. So Apophis and 2026 JH2 are the two ends of the same system. The big one we saw coming for decades, the small one we saw coming for a long weekend, and the regional devastation class, the 140-metre objects, the ones that are only about 40% catalogued, those sit in between, and which end of the warning spectrum any given one of them gives us is, right now, mostly luck. Did a survey happen to catch it on an earlier pass or not? That is the difference between years and days, and we are leaving it to chance. And think about what the Apophis case actually proves, because it cuts both ways, and the hopeful direction is real. Apophis proves that the warning problem is, in principle, solvable. When an object is bright enough and well placed enough to be caught early and tracked long, the system delivers exactly what you would want: years of lead time, a confident orbit, and the runway to act if acting were necessary. So the goal is not impossible. We are not up against a law of physics that says warning must always be short. We are up against the fact that our detection capability runs out at a certain brightness, and below that brightness the warning collapses from years to days. Apophis is on the bright side of that line. 2026 JH2 is on the dim side. The line itself is not fixed by nature. It is fixed by the instruments we have chosen to build and the ones we have chosen not to. Push the line dimmer with better telescopes, including instruments placed where they could finally look into the sunward corridor, and objects that currently give us a long weekend would start giving us years. The Apophis treatment, decades of warning, a calm, confident answer, is not a special case reserved for big rocks. It is what the small rocks could get to, if the detection line were pushed to where it needs to be. We have a working example of the system doing its job well. We just only get that example for the objects big enough to clear our current bar, and the bar is a choice, not a destiny. So here is the honest reading of the calm headline now that we have every piece. Newly discovered asteroid will safely pass Earth. Translated truthfully with nothing left out, it reads like this. We got lucky on the trajectory. We did not make this rock safe. The orbit it was already on was a miss, and we found it in time to confirm that it was a miss and to watch it go by. If the orbit had been the other kind, the warning we received those few days would have been the same few days, and they would have been a few days to watch, not a few days to act. We have proven once that we can nudge a rock. We have not built the thing that could nudge the rock that is actually coming. That is the gap. It is not a conspiracy, and it is not an oversight by any one person. It is just a thing that has not been built, sitting in the space where the most important machine humanity could construct ought to be. And the flyby this Monday, and the 7 or so others riding along with it this week, are the solar system doing what it has always done, sending the rocks through, letting the orbits converge, running the same accretion process that built the ground under your feet. The solar system's part is not going to change. Our part, the seeing and the doing, is the only part that was ever up to us. And right now the seeing has a blind spot and the doing does not exist. Part 8. The question that doesn't go away. On Monday afternoon, a rock the size of a building is going to pass between us and the moon, closer to Earth than much of the hardware we have put in space, and almost nobody is going to notice, and by Tuesday it will be gone, back into the dark, and the headlines will have moved on. And on the narrow question, the only question the headlines actually asked, 2026 JH2 is safe, and that is true, and you can let that particular rock go. I am not asking you to lie awake about Monday. Monday is fine. But I want to leave you with a question that does not go away when the rock does, because that is the real subject. That was always the real subject. The question is not, will 2026 JH2 hit Earth? It will not. The question is the one we started with, and we can state it now with everything underneath it. If the detection system that found this object is working exactly as it was designed to work, and working as designed still means a 70-foot asteroid can reach a quarter of the moon's distance with only days of warning, then what honestly happens the day the next one is not a near miss? We have walked through every piece of that. We know the catalogue is excellent for the giants, shaky for the city killers, and nearly empty for the size class that just flew past us. We know there is a blind spot in the sunward direction that ground-based telescopes physically cannot see into, and we know Chelyabinsk came in through exactly that blind spot, with zero warning in our lifetimes, over a city. We know that the 8 rock wave this week is not the 8 rocks that exist. It is the 8 that were bright enough and well placed enough to catch, the visible portion of a population whose other half we cannot see. We know that the convergence of those orbits on Earth's path is not an omen, but something far more permanent, the same accretion process that built the planets, and that has been resurfacing Earth with impacts for 4.5 billion years, a process that did not stop, that Earth is still inside. And we know that on the other side of the warning, on the question of what we do once we have seen, there is one proven tool that needs years of lead time, a warning system that frequently gives days and no operational capability standing in the gap between them. One science experiment, no fire department. And here is the thing I keep coming back to, the thing that I think is the actual weight of this story. Detection, the seeing, is the part that works. It is incomplete, it has the blind spot, but it is real, and it is improving, and every new survey telescope makes it better. The seeing is the success story of planetary defense. And even the success story, on its best day, performing exactly as designed, handed us a 70-foot rock with a long weekend of notice. That is the good half. That is the half that is going well. The other half, the doing, the turning of a warning into an action, that half is not incomplete. It is absent. It is a proven principle and an empty space where the machine should be. So the most truthful sentence anyone can say about an asteroid passing close on a Monday afternoon is not the one in the headline. It is not. It is safe. The most truthful sentence is, it is safe this time, and if it had not been, we could not have done anything, and we have known that, and we have not yet built the thing that would change it. The rocks keep coming. The orbits keep converging, because convergence is the rule that this solar system has always run on, not the exception. We just watched 8 of them go by in a week, and we will watch more, and almost all of them, the overwhelming, reassuring majority of them, will slide past in the dark and harm no one, exactly as 2026 JH2 will on Monday. But almost all is not all, and the only variable we were ever given a hand on, the only part of this that was ever ours to decide, is whether the gap between what we can see and what we can do gets closed before the trajectory that comes back around is the one that does not miss. That is the question. It does not go away when Monday's rock does. It is still there on Tuesday, and it will be there every week there is a wave, and it will keep being there, quietly, whether or not anyone is looking at it, until we either close it or run out of time to. And the strangest part, the part I will leave you to sit with, is that we are the first generation in the entire history of this planet that could see the question clearly enough to answer it, and also the generation that so far has chosen mostly to watch.